Welcome to Oceanography 2001. I'm Professor Nickel and I'll be guiding you through this class. You can hear the music in the background. It's something from when I was in college. It's called She Blinded Me with Science, and it's by Thomas Dolby. I'll make a reference to this song because I'm an old dad and it's kind of a dad joke, but I'd like to welcome you to this class. I hope you enjoy it. This lecture series will be used in the Oceanography online and blended programs here at St. Petersburg College. We're going to start off with science. What is science? You can see that we're going to talk about scientific measurements in the metric system and scientific inquiry. So that's the first topic we're going to look at. Scientific community uses standard units. Okay, now that is the International System of Units, or SI. That's the official name for the metric system. Now, when I was a kid, oh goodness, late 60s, early 70s, my teachers promised us we would be using the metric system in a short period of time here in America. They were wrong. We don't use the metric system. The United States uses referred to empirical units. Canada uses some. They're not 100% metric, and the UK aren't 100% metric, but they're they use it far more than we in America use it. But the scientific community across the world, even in America, uses the SI units. It's how you communicate with colleagues worldwide. You can see the base units. Now there's 7 basic units that all other units that we use are derived from. In length, the SI unit's the meter. Mass, it's the kilogram. Note it's not the gram, but the kilogram. It's 1,000 grams. The time is seconds. Electric current, the SI base unit is the amp or ampere. In temperature, the base unit is Kelvin. Fahrenheit and Celsius are derived from kelvins. In chemistry, the amount of a substance is the mole. Avogadro's number, the mole, is frequently used in chemistry. And then in optics, the intensity is candela, how bright something is. As I mentioned, all other units are derived. So if we're talking about speed or velocity, it's a distance over a time, a feet per second, a mile per hour. Now, those aren't the SI units. The SI units would be meters per second, but it's all derived from that. When you convert from empirical to metric, things get messy because the numbers aren't whole numbers. When you convert within the metric system, it's very easy because everything's based on 10. So it's just moving a decimal point. Giving the proper metric prefix tells you how many decimal points you have to move it. A giga is 9, one with 9 zeros. So if you're converting from meters to gigameters, which I don't know why, but bytes to gigabytes, you would move that decimal 9 times. A byte is a unit of measurement in computing. It's 1 unit of memory. I'm no computer expert, but that's my understanding. Mega is 6 zeros after the 1. Kilo is 1,000, 3 zeros after the 1, move the decimal point 3 places. Now, centi is 2 places because it's 2 zeros, it's 100. To the left, it's 100th. Milli, 1/1000th. In biology, micrometers, micrometers, nanometers, we use those for the size of cells, small microorganisms and such. So the metric prefix added to your base unit kilometers, 1,000 meters. Centigram, 1/100th of a gram. Milligrams, used in medicine, 1/1000th of a gram. That is the metric system, and that's why the metric system is easier than what we do normally. And I'm not going to put down what we do normally because I grew up and I understand it. And it means more to me than the metric system when you talk about temperature, speed, things like that, because I've used it my whole life. But studying in science, working in labs, you have to have a good understanding and good grasp of the metric system. There's that she blinded me with science. It was a little embarrassing when I was lecturing the other day and no one knew that song. So I had to play it for them in class, like I did for you in the opening. Science, the thing that I love about science is it's always changing. When you learn something new, you add to this knowledge. So you're understanding the natural world, you're making observations, you're testing these observations, you're adding to the knowledge and changing scientific knowledge. It's not like dogma where it is what it is, it's always been this way. It has to be testable. It has to be based on observable events. Now, that's where the whole science and religion comes in. I'm not going to open up that can of worms in class, except to say that you cannot test and observe all of the religious beliefs, no matter what religion you subscribe to, if any at all. So when you study science, you have to leave that part out because it's not clear and testable. It won't be affecting what we learn in class or science overall. So this problem-solving method that we use to explain our observations is called scientific method. What a surprise. Now, when you go on to higher education and you're going for a dissertation or a thesis, you use the scientific method to submit these. Marketing uses the scientific method to test their products on the public. So the scientific method is not just science, but what it does is it tests hypotheses in a systematic way that are repeatable, so you come with a definite conclusion. These results can be communicated, and everyone can do it repeatably the same way and presumably come up with the same results. It's based on observation. And observation, the hallmark of scientific study, is very unreliable. Take a look at that upper right-hand corner. You can see 3 lines, and just because of the arrangement of the arrowheads, the 3 lines look very different, although they're all the same length. So your observations can be unreliable. Just when you look at something, you need to learn to measure and remove bias. The picture below that is one of those hidden pictures, a picture within a picture. You can look at it and see an old lady. You can look at it and see a young lady. And the point is, everybody sees different things. My observation might be different from your observation, might be different from someone else's observation. So again, your observations, although it's the hallmark of science, need to be tested and bias needs to be removed. You start testing your observations by coming up with a hypothesis. Now, throughout most of your education, you've defined a hypothesis as an educated guess, but it's a lot more than that. It's a clear and testable blueprint to answer that question based on your observations. I prefer my hypotheses to be in an if-then statement, and that way it's clear and testable. If I add fertilizer to my daisies, then my daisies will grow faster during a given period of time. If I add fertilizer, there's my if. Then grow faster, there's my then. If, then, clear, testable. Then I have to set up my experiment. I'll need two groups. The first group is called the control group. That control group will have no fertilizer. I have to have something to compare the results. If I say it grows faster, I have to have a comparison. That control group is your comparison. Everything must be the same between control group and experimental group except the variable, what you're testing. The experimental group, I will add fertilizer according to the directions. That is the variable that I'm testing, the fertilizer. Does it work? We call the one you're testing the independent variable. The dependent variable are the results. So I add my fertilizer to one group. The next group has no fertilizer. The group that is given fertilizer, I measure the growth over a week, over 2 weeks. The group no fertilizer, I measure the growth. So now I have data. I don't look at it, I measure it, okay? So my observations are measured. Then I compare the results. The independent variable is the fertilizer. The dependent variable is the height that they grew in millimeters. Then I analyze that data and I come out with my conclusion. Does it support my hypothesis that they will grow faster? Just a quick review. The independent variable is what you're testing. It's what you change. The dependent variable depends on the use of the independent variable, and that's where it comes from, the dependence. That's what you're measuring, in this case, height in millimeters. If it cannot be observed, you cannot test it. If it's not measurable, you cannot test it. So science only deals with what is observable and what is measurable. There's 4 aspects of collecting data. The first is observation. Not the most reliable, but very important. The second is measuring, okay? In this case, you break out the ruler and you measure the height of your daisies. Samples. You have to have a large and random sample for each. Having 5 in the control group and 500 in your experimental group does not give you comparable results. A large group. Lastly, you have to take that data that you've measured and organize it in an understandable way, charts, tables, graphs, etc. Then you can come up with your conclusions. Sometimes you have to make a model. When I am looking at the movement of P&S waves through the mantle and entering the outer core, you can measure the data, measure the speed, measure the angle that it changes due to refraction or reflection. But being I can't cut open the earth and take a picture of it, I have to use models and make inferences. Sometimes what you're testing is too grand and you need to model and infer. Eventually, theories are formed. And theories are based on repetitive, tested experiments, and they change. A theory has the leeway to change based on new results. No experiment is a failure. For instance, Rogaine. Rogaine was meant to be a heart to help people with heart problems because it increases the blood flow. Uh, it didn't work very well, but it did increase body hair growth because it opened the blood vessels and replenished some of the hair growing cells. So it wasn't a complete failure. Even if it's a total flop in your eyes and does not prove your hypothesis and you think nothing comes from it, it's still not a failure because you have new knowledge. You can eliminate that hypothesis and move on to the next. So no experiment is a true failure. All experiments are observation of real events, and you come up with real knowledge and real data. The last and sometimes forgotten step is communicating the results. If you're making a paper or a presentation, a lot of times a senior thesis would be a paper turned in to graduate from some universities. Some psychology classes, you survey people and come up with papers or make a presentation to add to our knowledge base. Obviously, dissertations for PhDs or theses for masters add to our knowledge. Journals are published with new findings all of the time. So papers and presentations and communication of results is paramount. Also, repeatability is very, very important. I mentioned theories, and theories are explanations, and they're based on experiments, observations, and reasoning. They are flexible, though. When you come up with new information, theories must change. The experiments that you use to explain a theory need to be repeatable. Their theories are generally accepted by the majority of the scientific community. And a lot of times you cannot totally prove them, and that means they're flexible. There's room for growth in these theories. Laws, on the other hand, they basically summarize using mathematics. You can get a formula. It occurs without exception. Let's say Newton's laws of motion, the law of inertia, laws of gravity. These you can measure and come up with hard numbers and use it to calculate. They occur every time without exception. They're not the same as theories. They tell what happens, but they don't tell the why. The theories are the why. We'll move into the next topic, the history of oceanography. Now, early civilization was tied to water. I'm sure you've heard of the Fertile Crescent, the Tigris and Euphrates rivers. These rivers would overflow rich soil, provide water for crops and irrigation. At the end of the last ice age is when man first started to settle down. Movement through the Americas was based on the California current. The original Americans crossed into America from Asia, Siberia area, over the Bering Straits, the land bridge slash ice pack, and followed the California current down the west coast. We know that because we study middens. Midden, and there's a picture of a midden right there, are mounds. They're basically garbage dumps. Human civilization, human waste. Now you look at these middens and you find technology, different arrowheads, and different tools that were used. you find pottery and art showing beliefs and interactions with other communities. And you find food, what they ate, charred things if they had a grasp on how to use fire. And you can tell a lot about a society by studying its trash, the middens. So we study these middens and we find how early man was tied to the ocean for food and travel, trade. So oceanography started well before pen was put to paper, well before the aqualung scuba gear was made, well before navigation and ships. It started with early man itself. Spanning back, some of the early explorers include Egyptians and Mesopotamians, which used the ocean for trade. One of the first true maritime powers were the Minoans. Greeks and Phoenicians colonized the Mediterranean Sea. Polynesians were the first to um, travel in the South Pacific. Here's an ancient Grecian map. Uh, you can see they thought the whole world in this particular area revolved around the Mediterranean Sea because early explorers stayed close to land. You can get food, afraid of the unknown, many reasons, fall off the side of the world even, depending on the culture. Some cultures knew the world was round and proved it, and other cultures didn't. So staying close to land and not venturing too far, that's how early man dipped its toe, so to speak, into the ocean. As the toe was dipped into the ocean, man's curiosity led them to use science for the first time. And we credit and tip our cap to the ancient Greeks. And the ancient Greeks are what we feel science originated from. Aristotle was cataloging marine organism. Eratosthenes calculated the circumference of the earth. Maps and charts were made by the Polynesians, the Phoenicians, the Greeks. Ptolemy created the first atlas. Lighthouses in Alexandria, the original lighthouse, is one of the seven wonders of the world. And stars were charted and used for navigation and storytelling when you talk about the constellations. After Europeans, Europeans in the age of colonialism and imperialism led to a wave of discovery. Some of the more famous voyages, and we know Christopher Columbus, controversial nowadays, and rightfully so, but he was credited for most of American history as the discoverer of America. Now, we know when I mentioned those middens, there were people here well before Columbus. The original Americans crossed that land bridge. There was also Europeans. The Vikings actually traveled uh, to the Americas well before Columbus as well. And ironically, Columbus never set foot in North America, but he's still a prominent figure in the history of oceanography. Magellan, another prominent figure, although again, slightly less than you were told. He's credited with the first man to go around the world, but he didn't. He died before his voyage was finished, but being he set out and was the leader of the expedition, he gets credit for it, but he was killed in the Philippines before the world was circumnavigated. Captain James Cook was credited with the South Pacific and Pacific exploration. Remember now, the Polynesians were there first, but Cook was credited with being the great discoverer in the Pacific as far as Europe goes. Darwin, his famous Beagle trip, the HMS Beagle, he discovered new species, outlined the formation of coral atolls, and came up with a theory of natural selection that perhaps was the most influential ocean voyage of them all, because evolution stems from natural selection and Darwin's observations. So here are Captain Cook's 3 voyages. He was killed on his last voyage in Hawaii. There is Charles Darwin and a painting of the Beagle. And here is that voyage that Darwin took on the Beagle. And again, this was probably the most famous of the voyages because of natural selection, evolution, and the impact it's had on science. The first modern deep ocean scientific study was in the late 1800s from the HMS Challenger. They actually discovered the deepest point in the ocean. It's called the Challenger Deep, using cannonballs and ropes. It's in Marianas Trench. In 1925, the German Meteor expedition was one of the first to use echo sounding pings to map depth. It was very, very rudimentary then. Post-World War II, because really during World War II, echolocation made leaps and bounds because of submarines. So post-World War II, topographic maps were made of the ocean. We call them bathymetric maps when they're in water, and topographic maps on land. So the topography of the ocean floor was started after the echo sounding, and then plate tectonics was introduced in the early 1900s and poo-pooed at first, but as evidence piled up, it started to become more and more mainstream until eventually it was proven in the late 1960s. So that original Challenger, like I said, the Challenger Deep was discovered, and almost 4,500 species were discovered on this voyage. So it was a very important voyage in oceanography. In 1968, and I mentioned in the late 60s, plate tectonics was proven, and it was the Challenger again, except the Glomar Challenger, which was named in tribute from the original Challenger, was a retired oil drilling vessel, and deep sea cores were pulled up, and you could use fossil evidence and radiometric dating to show seafloor spreading, continental drift, and eventually plate tectonics. Some of the other inventions, the bathysphere, the deep sea submersible, Barton was credited with that in 1928, and Barton and Beebe descended over 3,000 feet beneath the ocean surface. Sonar, we mentioned, was used pre-World War II, but extensively during World War II for submarines, and then afterwards it was used to bathymetrically study the ocean floor. Scuba, Jacques Cousteau, and called it the aqualung, and he was very famous for using compressed air to study the ocean. Submersibles like Alvin were used to study the ocean ridge, the Titanic, and they're still used today. One of the things that I found really cool is you can measure and map the ocean floor from outer space. Sea level varies. The average sea level, day to day it might be different because of waves, atmospheric conditions, tides, but over a long period of time, using sea level, you can map the ocean floor because there's a 10-meter difference in sea level due to ocean floor topography. Over a deep sea hill, sea level is a little bit higher. Over a trench, sea level is a little bit lower. And you can use this data to map the ocean floor. And I found that to be fascinating, that sea level actually varies up to 10 meters, and it mirrors the topography of the ocean floor. As sensitive as our instruments are in outer space, they can be measured. Woods Hole, or WHOI, is the preeminent institute on the East Coast studying the Atlantic. Scripps is the preeminent West Coast institution studying the Pacific. Blanket is NOAA. Okay, so NOAA is the federal branch, covers the atmosphere and the ocean, and coordinates ocean studies. When we look at Earth's history, this is kind of an interesting map. The 7 seas. A sea is a partially isolated body of water. There's way more than 7 of them, by the way, but these are the original 7 seas that capture the imagination, if you will. When we talk about the history of our planet, and our ocean is 2/3 water, or our planet is 2/3 water, we have to go back about 14 billion years ago, okay, to the beginning. Did anything exist? Energy. That we, again, theory. Energy and matter are linked. You may have heard of relativity, E equals mc squared. So the Big Bang, or the advent of the universe, and that's a joke because it would have been a vacuum around that Big Bang and you wouldn't have heard the noise. But when scientists first introduced this theory, its opponents kind of called it the Big Bang mockingly, but it stuck. What you have is matter, and this matter, or what you have is energy, and this energy is expanding outward, and as it slows, matter. Okay, so the energy matter link, c is the speed of light, E equals mc squared. So you do have a link with the speed. This matter is forming clumps. These clumps are called nebula. It's dust clouds. In these nebula, you have subatomic particles, atoms. Hydrogen is the simplest atom. The universe is still mostly hydrogen. Hydrogen, when you have sufficient mass, fuses to form helium. That's what a star is. Most stars are hydrogen fusion factories fusing to helium, releasing energy. So the Big Bang and these steps are widely accepted based on scientific evidence. But of course, you're never going to be able to prove it without a time machine. And those don't exist. So some of the evidences discussed are the expanding universe. The expanding universe was measured by Hubble using the redshift. The abundance of light elements, especially hydrogen, helium, and these elements are being fused in stars at present and were fused within the first few minutes of the Big Bang. Cosmic microwave radiation and remnants heat left over by the Big Bang. Now, full disclosure, I am not an astrophysicist. So to me, I don't really have grasped the full concept of the creation or the start of the universe. You know, I can look at the evidence, I can explain it in a very rudimentary way for this energy to matter, and how the matter is expanding, and these little clumps of matter have a slightly different temperature, and they're pulled together by gravity, causing fusion. I can talk about how protostars become stars, and I understand that, and how planets are sweeping out their orbits in early solar systems, growing larger by a process called accretion. I can understand the solar nebula. I can understand planetary nebula, these gas and dust clouds that form full solar systems and planets coming from them. I can understand the life cycle of a star, but simple stuff, okay, because my background and my passion does not lie in astrophysics. But when we look at simple matter, quarks, and then subatomic particles, and then more complex, the atom, and then how the light, smaller atoms fuse to form the larger atoms, and eventually you come up with a planet, well, I can understand that linear thinking, how matter becomes more and more complex. Now, these systems of stars, interstellar matter, are clustered together in what we call galaxies. And when you look at the Hubble and the images that it has shown, you can see there's three basic type of galaxies. You have the elliptical, which tend to be the oldest in the outer reaches of the solar or of the universe, spiral, and then not fully formed irregular galaxy. And here's some images. The elliptical can be circular or cigar shaped like ellipses. The spirals have arms, and then the irregulars. Here's a picture of a nebula. This image from Hubble is called the Pillars of Creation. We can see the early signs of thermonuclear fusion, hydrogen being converted to helium, making stars. I mentioned the life cycle of a star, and let's just say the average life cycle of a star is the age of our universe, 14 billion years. Most stars, 90%, take the top path. We call them dwarf stars or average stars. The sun is a dwarf, and it goes through as it runs out of energy, red giant, planetary nebula, toward the end a white dwarf, and then it'll eventually burn out, brown dwarf, and then a cinder or black dwarf. The universe isn't quite old enough for that cindered black dwarf yet, so they're theoretical, or we just can't see them. A large, massive star, far more massive than our sun, could take a different path and in the end wind up as a neutron star or a black hole. And these life cycles take billions of years, upwards of the age of the universe itself. A little closer to home, how solar systems form. Now, we have pictures of all these sent back from the Hubble. They do take a long time, 4.6 billion years. Our solar system is that old. So we don't have observations of the process, but we have snapshots of different points of that process, and we put it in order and use the data to explain what happened. And there you have your inferences and your models. The upper left-hand corner, image A, is your solar nebula, and that nebula is collapsing. Toward the center, you have your protostar forming, like in B, and the swirling dust cloud spinning around that protostar. As you move to C and D, you can see orbits are starting to be swept out by planets. And then finally, a mature solar system in the bottom image have the planets swept out their paths, grown by accretion, and they're still moving in a flattened disk around their star. So that is how scientists look at solar system progression. Collapse, spinning, flattening, condensation into planets, and then planets growing by accretion. Those are the 5 steps outlined in that image before. Planets form in 3 steps. They start off as planetesimals, say that 3 times fast, move to terrestrial or gas giants. We are terrestrial, we're close to the sun. If you go to a gas giant, the core would be similar to a terrestrial, but then it's surrounded by gas. Now, early Earth would have been molten, it would have had to cool. Rocks started to form, solid rocks, about 3.75 billion years ago. That's the oldest rocks we found. Asteroids, meteorites, materials gathered from other places show the Earth and the solar system itself to be almost 4.6 billion years old. As a planet, including the Earth, cool, it gets stratified. Denser things tend to accumulate toward the center, and you have less dense closer to the surface you move. That's why our core is more metal and our crust is more silica. Density, stratification. Early Earth would not have had oxygen. That would have been added later on. You can see this image. You see an abundance of oxygen right around 2.5 billion years ago. That's called the oxygen revolution. Oxygen can be traced back over 3 billion years in small little pockets. How do we know about oxygen? Oxidation, rocks containing rust and other oxidants, iron oxide, they show the presence of oxygen. They're associated with microorganisms, fossils, microfossils. The link there is photosynthesis. The earliest life on Earth was likely photosynthetic, creating oxygen, thus opening the door for respiration and more complex life. The oceans themselves would have probably been formed by the outgassing and then raining, evaporation, until the Earth stabilized. So outgassing of volcanoes would have been where most of our oceans have come from. Uh, some of them, we probably got some water from cosmic sources, comets and impacts. Okay, so right now we do have 2/3 water. The earliest life, you can see little images of this filamentous bacteria. Photosynthetic. When I was in college, we called them blue-green algae. Since they have been reclassified as bacteria, not algae, and they are cyano, and cyano, incidentally, is blue-green, cyanobacteria. The oldest filaments are on the order of 3.5 billion, but they don't become overly abundant until a little later, and then that oxygen revolution, where it's clear and measurable worldwide, about 2.5 billion years ago. We still see them today in stromatolites. These are bacterial reefs. You can see the cross section of a gunflint shirt is a fossil assemblage, and full of these stromatolites. You can see their oxidation layers in the fossil cross section below the image. We're going to take a quick tour of our oceans now. Just look at each ocean and talk about some of the points, and that use this part of the lecture as point of reference for the rest of the class, because we're going to become familiar with a lot of the terms that I use. So here we have the physiographic chart of the ocean floor, Atlantic. A is the mid-Atlantic ridge. That is a divergent plate boundary. Don't worry, we'll learn about plate divergence. It's an underwater mountain range, seafloor spreading, volcanic, and it peaks above the ocean surface at point B, Iceland. C is where there's a mantle plume pushing up. That's the Bermuda rise. Bermuda is famous for the Bermuda Triangle, Bermuda Shorts. Now that Bermuda Triangle would be because there's currents diverging there, or converging, pardon me, converging currents. So it's stormy. There's that upwelling of mantle, so there's magnetic anomalies, volcanic activities, would have led to the legendary Bermuda Triangle. Also, they wear fancy shorts there. That's not a joke. Dress code. Those converging currents, that Gulf Stream that turns and feeds warm water. The southern part of that Bermuda has the northernmost reef-building coral because of that warm current. Now, those currents are steered around D, Cape Hatteras. We have the convergence of that cold and warm Labrador current and the cold Labrador current, the warm Gulf Stream, very stormy area, very famous coastal features, the Outer Banks of the Carolinas. The Gulf Coast, E, and I have a little circle there. I want you to look at the Gulf Coast. You can see how Florida is actually 2/3 larger, but that 2/3 is underwater. With the rise and fall of sea level, Florida would be larger and then smaller, just depending on where sea level is, where the ice caps are. So we have a broad shelf here on the Gulf Coast of Florida, hundreds of miles out until we get that steep drop off. The Caribbean Sea, again, partially isolated. This is the area of subduction in the Atlantic Ocean. Volcanic islands form that sea barrier. The Mediterranean Sea on the other side of the ocean. Look at how isolated it is through the Straits of Gibraltar, only several miles wide. And so this is a really isolated body. It's a huge sea. It'll be a Great Lake someday when that strait closes. And then in the southern hemisphere, we have the Trinidad Seamounts. A seamount is an extinct volcano that has moved off of the ocean ridge. So I use that as an example, seamounts. You can see along the sides you have latitude and longitude. The northern hemisphere is above the equator. The southern hemisphere is below. Make sure you put an N or an S. And then from the prime meridian, east of the prime meridian and wrapping around, and then west of the prime meridian. In the Pacific Ocean, we have the Ring of Fire. That's the plate, largest plate, Pacific plate. You have the spreading center here, East Pacific Rise. Here, the barrier reef holding a sea, another sea. This isn't volcanoes, this isn't land, it's a reef isolating the body of water, the Coral Sea. There's your Challenger Deep and the Marianas Trench. Japan is a volcanic island arc formed by subduction. We're going to learn about that. We have some seamounts there, and we already discussed that, the Emperor Seamounts. The Aleutian Islands, which are volcanic islands caused by subduction off of Alaska. The Bering Sea, the Bering Straits, that's where the original Americans crossed over. Hawaii is from a mantle plume upwelling. You can actually trace ancient plate movement by the direction of Hawaiian Islands and the seamounts. The San Andreas Fault is a transformed famous fault as the pressures push the Pacific plate in a northwesterly direction. The Galapagos is where Darwin, and we'll discuss the currents converge there. That's where Darwin's observations led him to postulate natural selection. And then the Andes, Peru, Chile's trench is a famous subduction boundary that we will study at length. In the Indian Ocean, we do have some highlights. Lake Baikal is a rift that's on a continent where two plates are, well, actually it's being pulled apart and a fault is forming. It's an old deep lake. It's the deepest lake in the world. The Black Sea formed at the end of the last ice age. Very interesting story. The Caspian Sea used to be connected, but now it's a big salt lake. The Red Sea is a future. It's embryonic. It's our ocean starting to form. We have Africa drifting apart from Asia there, forming a new ocean. The Seychelles are the only granitic continental islands in the oceans. Madagascar is one of the older islands, and it's the second largest island next to Australia. It's very, very famous for endemic species found nowhere else on Earth. Prince Edward Island is really a crazy example of man gone wrong. When it was first settled, rats on the ship overtook the island. So what they did was they brought cats to the island. Well, cats were eating the rats, but then when they started running low on rats, they started killing the endemic birds. So they had to get rid of the cats, so they introduced a virus to kill the cats, but it didn't kill all the cats, it only killed some of the cats, and the cats that were left were super cats, and they were killing the birds at a greater rate. So they basically had to come in and physically remove the cats. Kind of a crazy story. Exotic species. Introduction of exotics is one of the ways man harms the environment. There's our Indian Ridge, and one of the famous trenches here from subduction, we'll learn about trench formation. There was a huge tsunami here, the Christmas tsunami, that unfortunately over 250,000 people perished over the holiday season, and we'll talk about tsunamis and that particular tsunami later in the course. We're going to wrap up today's lesson with a quick review of cartography. And we looked at a couple of the old maps, Grecian maps, but really most of the knowledge of the planet was housed in the library at Alexandria, Egypt. Unfortunately, that library burned down. Many human historians look at that as the spark of the Dark Ages in Europe and a whole bunch of unrest. But the library burned down and many of our ancient knowledge was lost. Eratosthenes, we mentioned, he calculated the circumference of the Earth. He invented latitude and longitude system. He was a librarian, so he was a famous. And then celestial navigation were invented at this library. So the library housed all these charts and all this ancient knowledge. It was lost. But latitude and longitude, the angular distance north or south of the equator. The equator makes logical sense. It's where the sun is directly overhead, 90 degrees, during the equinoxes. It gets 12 hours day and 12-hour night year round. Longitude is north or east or west of the prime meridian, which was decided on by international agreement, runs through Greenwich, England. So it doesn't have that perfect sun equinox. It's just, it was randomly decided upon. The Earth spins 15 degrees per hour, which means each 15 degrees of longitude is one time zone. The angle, the height of Polaris in the northern hemisphere is your latitude. Latitude is the height of Polaris above the horizon. So ancients used that to navigate. The study of the deep ocean and these charts and maps are called bathymetric. Here's a bathymetric chart. We looked at bathymetric charts when we surveyed the ocean, but here's the Gulf, wide continental shelf, continental slope down to the deep ocean. Continental shelves are made of the same material continents are. We call that granite. It's a very high in quartz rock. The ocean floors are made of basaltic type rocks, low in quartz. You can see how wide this shelf is. There's our latitude and longitude. Notice these little, those are minutes. A degree of latitude is broken up into 60 minutes, much like an hour is broken up into 60 minutes. So 2730 would be 27 and a half degrees. 2845, that would be 3/4 degree, 45. So it operates much like time. The lines that connect equal depth are called isobaths. We draw isobaths using sound readings. Here's the 5-foot isobath in this case around Anclote Key. the lines can't cross each other. This one I drew myself. Most harbor charts use 6-foot contour lines, not 5 like I drew, but 6. And that's because 6 feet is a traditional measure of depth called the fathom. NOAA charts all navigable waters, gives you bathymetric. We use them to study the nature of the coast, the depths of the water, the configuration of sea bottoms, rise and fall of the tides, danger, man-made aids like buoys, and magnetism and how magnetism changes. NOAA charts are used for transportation, engineering, naval operations, and recreation. You can go to a West Marine store and buy a chart with locations of good fishing areas. It'll actually have pictures of little fish and where to find them. Here, 12 nautical miles, and a nautical mile comes from 1 minute of latitude, where a statute mile is an empirical unit. Nautical mile is a standard 1 minute of latitude unit. So 12, and that's our territory. After that, you have some of our laws apply, but not all. And then out to 200 miles, we own the mineral rights, but these are international waters. The Great Lakes are also charted because they are navigable waters. The nautical mile we mentioned, they're used on ocean and coastal. Statute miles, intracoastal waterway, Great Lakes, land. Meters outside of the US, and fathoms are traditional units. A lot of times isobaths are drawn in fathoms. By the way, a nautical mile, or 1/60th of a degree, is equal to over 6,000 feet. So a statute mile is shorter than a nautical mile. It's 87% of a nautical mile. Here is a large scale chart used to plan routes. There's Pinellas County, there's us. This is more of a local chart. You can go buy this chart and the isobaths will be drawn, and you can use this for a lot of detail. Harbor charts show even more detail. If you get a nice harbor chart, you can see how it's shaded in blue, and then where it's white, you don't really have to worry about. Even a large ship can travel through there. You have buoys depicted. You have your lines, and these lines, there's 12-foot contour. They are done at the 6-foot intervals. So there's your 6-foot intervals: 6, 12, 18, 30, and then you stop because it's deep enough for ships to pass. All chart data comes from the mean low water mark. During super tides, it might get a little bit more shallow, so you need to check, but it's the mean low water mark. That's where the isobaths are drawn from. And they are every 6 feet. The isobaths are every 6 feet, contour lines. Lastly, you have a compass rose. The compass rose shows you geographic north, where the North Pole is, and magnetic north, where your compass is. They do not match. Magnetic north is not exactly at the North Pole. Furthermore, it wanders. So it increases here 2 minutes, and its variance is 12 degrees, 15 minutes. So basically, your compasses don't point to geographic north, they point to magnetic north, and you need to account for this difference. Now, of course, a GPS accounts for it automatically, but if you were navigating using a chart, you would have to account for this difference. It also changes, rendering charts useless after a decade or so, because you have a 2-minute increase every year to this variance. That summarizes chart and cartography. Well, that's the end of our first lesson. I hope you enjoyed Module 1. I look forward to bringing you the remaining modules. Have a great day, folks. It's a pleasure working with you.